People may roll in while we're presenting, but that's all right. All right, so good afternoon, everyone. My name is Connor Waybright. Thank you for joining our Spring 2021 Capstone presentation. Throughout the semester, my team and I have been working with Istituto Superiore di Sanità, or ISS. We've had the privilege of working with Christina Parenti, a consultant who works with ISS, along with Dr. Olga Cheraminskaya, Dr. Cecilia Bosa, and Dr. Chiara Battistelli. ISS is the National Institute of Health located in Rome, Italy. They were founded in 1934 and have since become the main center for scientific research on public health in Italy, with 2,300 people, including researchers, technicians, and administrative staff, working daily to protect citizens' health. ISS consists of 6 departments. That's food safety, infectious disease, neuroscience, oncology and molecular medicine, cardiovascular, and finally, the Department of Environment and Health, or DAMSA. And this is the department that we've been working with for the past year or so. Our goal today in presenting this information is to give our audience a better understanding of what ISS does, and more specifically, how they're working to create solutions to some of the issues faced in modern toxicology. Today, we're going to introduce you to some of the data and accessibility problems impacting modern toxicology. We'll propose a solution to these problems, and then we'll discuss the system that we've designed to address these problems. My name is Connor Waybright, project manager of this team. I've had the pleasure of working with my teammates Ryan Brim, Yuklin Ong, Brandon Ward, and William Warner. Thank you for joining us, and I'll now let Ryan introduce you more to the ISS Department of Environment and Health.
Thanks, Connor. So along with DAMSA and the 5 other departments she's mentioned, ISS is divided into 16 national centers, 2 reference centers, 5 technical scientific service centers, and a notified body. The Department of Environment and Health conducts research and experimentation to analyze the effects of social and environmental risk factors. This includes environmental monitoring studies, biomonitoring of human populations, and more. DAMSA also uses these studies to protect and maintain the environment to reduce diseases caused by these risk factors. The World Health Organization estimates nearly 1 in 4 deaths could be traced back to environmental risk factors which contribute to these diseases. ISS and DAMSA are dedicated to decreasing the number of deaths by reducing risk factors that they're studying. And this project we're presenting today will assist DAMSA in this goal. So DAMSA has been working on this project called ISTOX for about 20 years now, and it's a collection of 5 data sources created by many ISS researchers, including Dr. Benigni, Dr. Battistelli, Dr. Bosa, Dr. Cheraminskaya, and Dr. Kretis. Currently, Dr. Bosa and Dr. Battistelli are working to maintain the data source to make sure that it includes correct information. And here on the slide, you can see the fishbone diagram that we've created to identify problems that prevent effective use of toxicological information. Some of the main problems include people, material, method, and environment. So for people, these problems are centered around the fact that most people don't have a background in coding, so they can't really effectively search the database using SQL. This is one of the reasons is there's also poor accessibility to the data. For material, these stem from data quality issues. There's headers that aren't standardized, and so there's less interoperability between the data. For method, there's not really a method for searching for the data. So users currently download the Excel sheets, these 5 data sources, and then they search across the data however they like. So there's not really a standard method or flow to searching. And lastly, environment. The problems in this category are mainly animal testing, which y'all can go into more now.
All right, thanks, Ryan. So ISS supplied our team with a document called New Perspective on Toxicological Information Management, or we prefer to call it as the New Perspective document. This document provides us with details about the state of toxicology today, including how recent legislation has globally impacted modern toxicology. So over the last 15 years, the European Union, also known as EU, has introduced new policy known as REACH. REACH stands for Registration, Evaluation, Authorization, and Restriction of Chemical. According to our research on REACH, this legislation impacts many companies across the EU as it applies to all chemical substances, both in the industrial and in the household product. REACH is also intended to reduce animal testing of harmful chemical. This and other international legislation to reduce animal testing create high demand for a robust toxicological database that will store all the existing experimental data. To achieve this goal, ISS has consolidated the existing sources into field database. The figure shown in this slide is an example of one of these databases. This database sometimes contains incomplete or contradictory data, and the vocabulary is currently unstandardized. We will discuss how our team helped ISS to address this issue later on in the slide. I will next talk more about the toxicological database. So what exactly is a toxicological database and why it is important? A toxicological database is an organized collection of data related to toxicity of chemical. Toxicological databases are utilized for safety and risk analysis of chemical, product discovery and development, and academic research in biomedical and toxicological science. As Ryan mentioned, ISS started a project called ISTOX or ISS Talks. This database will contain 5 different data sources, and each of the data sources will contain different information. For example, ISS CAN contains chemical carcinogen, while ISS Bio contains carcinogenicity and mutagenicity of biocide. The reason ISS started the project is to provide a user-friendly, standardized collection of useful data that will be available to the public at the end. This project was a helpful step in solving all the problems Ryan and I mentioned in previous slide, but currently it is not finished yet. In the new perspective document, ISS details their need for analysis features built into the database, and they discuss their goal of arranging data into a single relational database. Both of these features are currently missing. So all the data currently is either stored in Excel file or .sdf file. This will create data integrity problem, which including updating and deletion issue. Another problem storing this data is contradictory data might exist. For example, this chemical might exist in ISS MIC and ISS CAN with 2 different chemical names. Because the system does not automatically update, the possibility for data integrity violation is high, and this will compound the updating issue and deletion issue. I'll next pass to Brendan to talk more about the system that we are designing.
Thanks, Yak. According to the New Perspectives document supplied to us by ISS and through numerous stakeholder interviews with ISS, our team determined that the functions of this system can be broken up into 4 main subsystems. These subsystems are the database, the user interface or UI, analysis, and visualization. Each of these subsystems is designed with specific functions that are aimed at meeting the stakeholder needs and solving the issues that we've discussed previously. Next, I'm going to move on to how we determined each of the necessary functions. We conducted stakeholder interviews through conversations and emails with ISS and industrial engineering faculty members to determine the necessary requirements of the system. Outside of ISS, we researched similar existing systems to generate ideas for functionalities that should be included. We determined that there were 13 functions that could be divided up into the 4 subsystems that could address all the concerns and meet the needs of ISS. This is our minimum viable product, or MVP. After we determined these 13 requirements, we met with ISS to understand how they viewed the importance of each of the functions. These priorities were then scaled to depict the relative weight or importance of each function, and this is called our perceived user value, or PUV. As you can see on the graphic in the bottom left, the user interface subsystem is weighted the highest, and this is because ISS has a high demand for having a very accessible system for public users. Next, Ryan is going to go into some more detail about how each function is going to be executed, starting with the database subsystem.
Thanks, Brandon. In developing the database subsystem, we identified 4 objectives we knew we had to meet in order to satisfy stakeholder needs. First, we needed to create a relational database. This requires fixing missing and poor quality toxicity data. Second, we knew the data had to be exportable. We knew that headers needed to be standardized, and then we needed to create clear definitions of these new data headers. So to accomplish these objectives, the tool we designed has to be based on a single database model. This requires normalized standardized data, which involves making sure any null values are defined, each row only has one entry per column, headers are standardized across each relation, and many other fixes. We also determined that we needed to organize the roughly 150 headers and condense them down based on the information they contain. To do this, we used OECD, Organization for Economic Cooperation and Development's templates, to standardize the headers and used an entity relationship diagram, ERD, to represent the arrangement of the entities and the relationships in our data model. Moving on, we'll discuss some of the objectives with the user interface subsystem. We knew a functional UI is an essential component to improve the user experience with the current data. We also knew that this interface should be accessible through the internet and allow users to view the data along with the results of their queries, analyses, and basic data visualizations. And because of the potential lack of SQL experience in our end user, we wanted to be able to have them be able to search through our database without typing it in SQL, which is the coding language of the database. And to do this, we'll create a bunch of buttons, field search bars, and drop-down menus in order for the users to navigate through this. This UI should improve the user's experience with navigating and analyzing the current data that they have. Now we're going to go into more about the data analysis and data visualization subsystems.
Thanks, Ryan. So one of the most important features of this analysis subsystem is that it can increase its tox capability by estimating chemical toxicity. So according to ISS researchers, structural similarity is a useful predictor for many chemical effects, including toxicity. And so with this being understood, this system must be capable of grouping chemicals together based on their chemical structure. Structural information will be stored in the form of a simplified molecular input line entry system, or SMILES code, in this database. And a SMILES code is just a notation that allows users to represent the structure of a molecule as a string. So the analysis subsystem should also allow users to input the SMILES code of a chemical that does not exist in the database. And then the subsystem will find structural analogs with known toxicities within the database and use those values to estimate the toxicity of the input chemical. So the overall purpose of this subsystem is to help researchers estimate the toxicity of chemicals to reduce the need for animal testing. And moving forward, I'll talk a little bit more about our visualization component of this. The visualization component is just aiming to increase the usability of the system, giving users more information about the data without the need to export the data and manipulate the data elsewhere. We worked with ISS to determine the most useful graphics to display within the system, and through conversations with researchers at ISS, we determined that this subsystem must be capable of displaying 2D molecular structures based on a user input SMILES code. To implement this subsystem, we recommend the use of Java to receive a user input SMILES code corresponding to a particular chemical, and then output the associated 2D molecular structure. And now I'm going to pass it back over to Connor to begin discussing our system design process.
Thanks, Will. So I'm going to talk a bit about the progress we made in designing and implementing this system. And so as we mentioned before, the original ISTOX data needed some cleaning and reformatting before it could be fully utilized in a single relational database. Our mission is to increase the interoperability of and accessibility to this toxicological data. And one important step in this process is to standardize the data. The process of standardization requires our team to search through the data from the original ISTOX headers and find all unique attributes or headers from the original data. We needed to define those attributes, which I'll talk a bit more about how we did that on the next slide. And we needed to update the header name to match OECD template terminology. OECD is the Organization for Economic Development and Cooperation, as Ryan mentioned earlier. And the reason we use OECD is because it is internationally recognized terminology. And so it helps improve the accessibility of the data by allowing a broader base of users to understand it. And so as we went through and updated the header names, we made sure to store the original ISTOX headers in an Excel sheet to ensure that we can retrace the new name back to the original name. And so next I'll talk a bit more about how we identified all the attributes and how we cleaned and stored the original ISTOX data. So one of the challenges that we faced during this process was determining exactly what headers exist in the ISTOX dataset. There were many cases of headers existing as a combination of multiple values, like the rat male cancer header in the old headers table, that's the blue table. This header stores the values rat, male, and cancer all in the same header. But in a normalized relational database, headers should be stored as the attributes should be stored as headers, and the entity, the instances of the entity should be stored in the rows. But we see here that it's kind of backwards. We see that the old headers are storing instances of the entity, and the rows only store the substance ID and the test result. Storing the data in the format of the old headers here creates many no data cells. Those are all the ND cells in the blue table, and this makes for an inefficient database. And the reason it creates these ND or no data cells is because not every substance is related to the test instance that is stored in that column. So for example, the rat female cancer column in the old headers table, look at substance 2, that's the second row. It contains the value ND. This is because substance 2 never had a test done on a female rat for cancer. But the cell must exist because another substance, in this case substance 1, did have that test performed. So when storing instances of a test in the headers, entries must be made in every single row of that column, regardless of if there was a test done on that substance or not. So all of these ND cells make the original data quite inefficient. And so to fix this problem, we analyzed all the existing headers to determine what entity attributes actually exist in the data. And so for example, in the original header, rat male cancer, rat is a value for the attribute species, male is a value for the attribute sex, and cancer or carcinogenicity is a value for the attribute toxicity type. So after defining all of these attributes, which are species, sex, and toxicity type, we added them into the headers and we transposed the values, rat, male, and carcinogenicity into the rows. And so what we're left with is less ND cells and a more efficient database. Another added benefit of this particular solution is that it makes it much easier to search through the data for any particular attribute or value, because now the values and attributes are all separated out. And so along with cleaning the data, we also had to normalize it to store it in a relational database. And the biggest problem we found in the original ISTOX data was that there were many cases of multiple values being stored in a single cell. So if you look in the blue table, all of those synonyms are stored in one cell. We wanted to achieve first normal form with this data, but having multiple data entries in a single cell violates first normal form. So to fix the problem, each attribute that had multiple entries stored in a single cell was split into its own table. And so a good example of this is the synonyms attribute shown on the slide, where a synonym, one chemical name can have multiple synonyms associated with it. And the original data sets stored all of those synonyms in a single cell for a given chemical name. So to fix the problem, we created a synonyms entity and assigned a unique ID to each row. So the common name and the synonyms are still related to each other, but we no longer need to store multiple synonyms in the same cell. There were many other attributes in the database and the original data that had this problem, and we solved all of them in a similar manner. Splitting these attributes into their own tables was an important step in designing a normalized data model, and Yak's going to tell you more about our process of designing that data model.
All right, thanks, Connor. Initially, we got a data model from ISS that contained 3 entities or tables which are the substance table, the test condition table, and the test result table. We then break them into multiple tables to address the normalization issue that Connor mentioned in the previous slide. So currently the finalized model contains 10 tables in total. The design of this model was inspired by the STAR schema, which consists of one large central table and multiple dimension table that radiate from the central table. The central table is called the fact table, which in our case will be the substance table on the top center position in this slide, while the dimension table will be the rest of the tables. If we look at the top left corner, the synonym tables, you will realize that there is PK and FK right beside the synonym IDs and the substance ID. PK is the acronym of primary key, which means this key works as an unique identifier of the entity or table. In this table, synonym ID will be the primary key for the table. So for FK, it stands for foreign key, which can be defined as the key that taken from one table and put into another table in order to create a relationship. So in this case, the key substance ID was taken from the substance table and put into the synonym table to create a relationship. As you can see from this slide, there are lines connected between two tables. So this line represent the cardinality relationship. There are total two different relationships in our model, which are many-to-many and one-to-many. If we look at the relationship between the substance table and substance dataset table located on at the top center position in this slide, it is a many-to-many relationship, which means one chemical might exist in multiple datasets and one dataset might consist different chemical. So if we put our focus on the bottom left corner in this line, the test condition table and the test result table, the relationship between these two tables is one-to-many, which means a set of test condition can apply to many results and one test result can only have one set of test condition. If we look at the information contained in the test condition table, you will realize that lots of attribute names ended with enum. Enum stands for enumerated data type, which is a set of value that is predefined. One example of the enumerated data type would be the species in the test condition table. The domain or pick list value for this attribute species will be rat, hamster, and mouse. When the database administrator or the data editor input the data into the database, they must choose the value from the list if the attribute is a enumerated data type. So they couldn't input any information they want. For example, input a cat or dog for that data or information because this value does not exist in the list. So we will next move to the proof of concept that our team creates. So in order to test the data model that I just presented, we created a proof of concept using Microsoft Access. And this is recommended by Dr. Rossetti, an INAC professor in our university. The reason we create the proof of concept is to perform an error checking for our model. In the proof of concept, it will contain a small portion of the data after those data has been cleaned and normalized. So in this slide, we can see that extra table created compared to the previous ERD model, which there are total 15 tables in total. So the reason that this additional table were created in this proof of concept is because Microsoft Access does not allow direct many-to-many relationship to be defined. So we have to use a junction table or an associative entity to create a relationship. A junction table will contain the primary key from two or more tables in order to relate this table together. An example of the junction table will be the substance use type table located on the top right corner. So in this table, you can see that it contains the primary key of substance table and the use type table. I'll next pass to Brendan to talk more about the UI.
Thanks, Jock. So to ensure that we could fully accommodate the requirements and preferences that ISS had for the system, we used a process of iterative feedback to design a user interface mockup. Using Adobe XD, which is a user experience design tool, we designed features and functions that we believed would exist in the system and add value, and then showed that design to ISS to allow them to suggest any changes and clarify any confusion that we might have had. This process worked really well. It allowed ISS to visualize each function that we were trying to discuss and say exactly what they need or want, rather than trying to talk about things in abstract ideas. While developing this mockup, we focused on designing standard workflows that public users would follow while conducting searches and analyses. One function that Dr. Kim Needy and ISS agreed was very important for this type of system that would exist publicly accessibly was user authentication. The graphic on screen shows the need for credentials if a user wants to sign in as an administrator. Administrators within databases have special privileges that general users do not. For example, a user or an administrator can add new data to the system or manipulate the data model. Requiring these users to sign in prevents unauthorized users from damaging the integrity and quality of the data, which could have potentially disastrous effects if that modified information was taken into consideration when making legislative decisions, for example. Moving on, let's talk about making searches using our system. In order to conduct the main types of searches within this system, the user must know some identifier of the chemical that they want to search for. This can be the chemical's name, the molecular formula, the structure, or something else. The menu on screen shows how users can input structural information about their chemical. While talking with ISS, we learned that some users of the system will not know all the identifiers of a chemical, and it would increase the usability to allow those users to draw the chemical structure of the chemical that they're trying to search for, and then use that drawing to conduct a search. And the menu on screen, of course, facilitates that functionality within our mockup. After a user has identified the structure that they want to search for, this menu also enables 3 types of searches. First of all, a user can search for information about the single chemical that they've entered using the exact match button. Next, users can click on the substructures button if they want to search for all chemicals with structures that contain the input substructure. And finally, users can select the structural similarity search option and then input a similarity level or a specific number of analogs to the chemical that they want to see, and then receive those results. The next step for users of our system is to add the filters that are shown in the filters window on the right. Filters can be applied to searches using the filter list and the search conditions menu shown on the left of this slide. There are options within this design to filter a search using most of the attributes within the data model. Alongside these filters is the ability to combine searches using the logic operators and an OR. This feature was something that we saw in a lot of other similar chemical databases, and since it allows users to customize their search in more complex but still very useful ways, we thought it would be useful to include it. And through the use of these filters and operators, the system will be able to formulate complex queries on the database without requiring the user to ever type in any actual query language. The final feature of the menu shown on screen is the storage of previous searches. This feature enables the use of our logical operators, and it allows users to quickly compare their search results. Through this menu, users are also able to go back into a search and modify the search filters if they realize that the results were not accurate after receiving them. Next, Will is going to talk about the next step after clicking View Results.
Thanks, Brandon. So as I mentioned earlier, ISS required the ability to view reports online and export data. So after the user presses view results, like Brandon mentioned, and they arrive at the final result screen, they're presented with 2 options, view report and export data. So when the user selects view report, they will view all the information online in a useful format that contains structures, SMILES code, and other chemical attributes. The report view also summarizes the toxicological test results from the chemicals in the search. And this is important because it allows researchers to make an estimate of the toxicity of similarly structured chemicals. So now let's suppose the user wanted to select export data. This would allow the user to export the data in their preferred format, such as a CSV file, XLS, or PDF. And by allowing the user to have multiple options as to how they can manipulate searches, view the data, and export it, we're providing ISS with a robust system design that can meet their needs. And now I'll move on to how we evaluated the performance of our user interface prototype compared to the original search process. So as with any system design, we needed to validate that what we designed with our UI would show improvement in how substances were searched for. Originally, data was split between 5 different data sets, and there really wasn't any possible way to search by substructure. So with our new system design, we streamlined the process of searching for substructures or substances and the information related to substances, and we provided the ability to search for substructures. So to collect meaningful data to demonstrate the predicted improvement, we had to use metrics that could be observed not only in the original Excel formatted data sets, but also in our Adobe XD prototype. So we determined that the 2 most useful metrics for this comparison were the number of clicks it took to find a result and the time it took to find those same results. And so through these metrics, you can see that we showed an increase in efficiency, which resulted in less clicks and less time for each search. The blue bars on the screen represent the original system, and the yellow bars represent our UI prototype. And after these comparisons were complete and documented, we showed at least a 65% reduction in number of clicks and time to complete a search for a substance. So moving forward, I'll talk about what we'll be giving a future implementation team. So given that this is a system design project and our scope doesn't include full implementation, we had to be really thorough in how we documented our work. From conceptualization to problem definition to system design, we recorded every decision that we made in technical documents that will be passed on to an implementation team in the future. These documents have been written to help a future team understand the system and how the design meets stakeholder requirements. And on top of these documents, we'll pass on to the implementation team our Adobe XD UI prototype, which serves as an interactive visual representation of the user interface. We will also provide a use case and requirements document detailing how each feature in the system is to function, including descriptions of each anticipated use case. We'll provide our prototype data model and Microsoft Access to serve as a guide for how to develop the model in the future. And then lastly, we'll provide our PUV and MVP to help guide the implementation team's development of this project. And now I'll pass it back up to Connor to wrap up our presentation today.
All right, thanks, Will. So our industry partner is in Rome, and is about 7 hours ahead of us. So they recorded a video discussing the potential impact of the system we designed and then their experience with the University of Arkansas. So I'm going to play that video now. And if you can't hear it, let me know and I'll adjust that.
Thank you, Dr. Cassidy, for having us here today. My name is Cristina Parenti, and I had the pleasure to work both with the industry partner, the Istituto Superiore di Sanità, and the University of Arkansas Rome program. We're very excited for this present and future collaboration, and I found the students to be very engaged, and Dr. Schubert's insight was crucial for the achievement of the goals. I will let the industry partner directly explain better how the students reach their goals, and thank you again to everybody involved in this study.
Thank you, Cristina. My name is Olga Cheremenskaya, and I'm from Istituto Superiore di Sanità, which is the Italian National Institute of Health. It was our first year of collaboration with the University of Arkansas, and I would like to say that it was a very positive and exciting experience. The main goal of the project was to further development the ISS Tox database clusters developed by our group at the ISS during the last 20 years. The students have analyzed, cleaned, and standardized the data according to OECD harmonized template terminology. And in addition, a data model suitable for storage and retrieving of data have been developed by the student. And the narrative description of possible open web interface of future web application have been also designed. The potential impact of this project would be to use the standardized data for developing of computational toxicology methodologies, which became extremely important in the last years because the main regulatory agency required to reduce animal testing to absolute minimum. So to address predictive toxicology need and also industry needs and scientific needs, it's extremely important to make data findable, accessible, interoperable and reusable in much extent possible. I would like to take this opportunity to thank Dr. Cassidy and Dr. Schubert from Arkansas University, to thank my colleagues Cecilia Bosa-Chiara-Battistelli and Alessandro Giuliani, and Giuseppina Mandarino from External Relations Office of Istituto Superiore di Sanità. We are looking forward to continue our collaboration with the University of Arkansas in the next years.
Thank you.
Thank you.
So our mission was to increase the interoperability of and accessibility to the original ISTOX data. The most important aspect of this mission was to make the data more accessible and easier to navigate. In an effort to reach this goal, we created a data model sufficient to store all of the original data, and we implemented that model into Microsoft Access to verify that it stores and retrieves the data effectively. To further increase accessibility to this data, it was determined that a public online user interface would be beneficial for users. So we used an iterative design process working closely with ISS to ensure that our UI design met their requirements. We created an interactive proof of concept of the design using Adobe XD, which allows our stakeholders and future development teams to click through the system to better understand the required flows of our design. And finally, we compared the efficiency of conducting toxicological data searches with the original system versus our new system, and we found that our design reduces the number of clicks and the amount of time required for each type of search by at least 65%. Looking forward to handing over our prototypes and documentation to the next team to further develop the ISTOX project. And on behalf of my team, we'd like to thank the University of Arkansas and ISS for giving us the opportunity to work on such a unique and challenging project. And now we will take any questions or comments from anybody listening to the presentation. Thank you. Okay, if there's no questions or comments or anything, we will be moving back to the other link on the website, the exhibition link. And there we have a poster that summarizes all the work that we did. And it's more of a, a conversational place, virtual room. So you can ask us any questions about anything and we can give you a quick overview of everything we've done so far. But we'll be back on that exhibition link in about 20 minutes if anybody wants to join us there after this.